So welcome back to yet another video of this well-structured and comprehensive machine learning bootcamp. This is going to be the part 2 of this tutorial, and if you haven't watched the part 1, do check out, it's really nice. This video is very important as it's going to cover the important and fundamental concepts of our upcoming tutorials. So without any delay, let's code up and get started. In this video, we will cover types of variables, what is regression and types of regression models, training, test, validation set, feature scaling, R-square and adjusted R-square, and last but not the least, main challenges of machine learning. Types of variables in a data set. So there are two types of variables. One is dependent and one is independent. The dependent variable is depending on in this independent variable, the values according to the value of this independent variable, the value of dependent variable is going to change. So right, independent variable is also called as feature or predictor, as it predicts the value of dependent variable, and dependent variable is also called as a label. So what is regression? Regression gives the relationship between dependent variable and independent variable. So we can find the relation of these variables through an regression equation. What's the importance of finding the relation? With this relation we can find the predicted values of independent variables, given that we are having dependent variables, right? So let me give you an example of this dependent and independent variable. Here, years of experience. This is a simple linear equation, simple linear regression data. So in here there are only two uh, two columns. One column is of the independent variable and the second column is of dependent variable. So years of experience, according to the years of experience, the salary is decided. So here this is independent variable and this is dependent variable. According to this is going to be decided, right? So if you are 1.1 years have if you have so if you have 1.1 years of experience, the salary is this much, and so on. So if we find the relation between this and this, we can find we can find for the years of experience of 11 years, we can find the predicted value of the salary. So if we find the relation, we can predict for more number of years. So that's why we need a regression equation. So types of regression models, machine learning models we are going to cover in this video. Simple linear regression, as we have seen, this is the simple linear regression, as it has only two variables. One is dependent and one is independent. Multiple linear equation. In multiple linear equation we have more than one independent variable and one dependent variable, and so on. Polynomial regression, support vector regression, decision tree regression, random forest regression, and so on. In the future videos, I will give a detailed explanation of each and every regression model, right? So training, test, and validation set. Yeah, let us say this is our data set, right? And this data set is divided into two parts: training set, on which the machine is going to be trained, and the training set in which we test the predicted value of dependent variable with the test value of the dependent variable. So to find the accuracy of our regression model. So validation set, mostly validation set is used to tune the hyperparameters, and we'll discuss what are hyperparameters in the next video. I'm not going to discuss about hyperparameters, because this is only going to cause confusion, right? You don't need to know it right now. So this is validation. So remember, validation is a subset of training set and is used to tune hyperparameters such that to make our machine learning model more better. So that's why we need validation set. I'll explain in detail about validation set in the upcoming videos. So this is the training set and this is the test set. So what is feature scaling? So what happens in multi-linear so feature scaling, what happens in multi-linear regression models is that some variables, some independent variables have more dominancy over other independent variables, and so that independent variable dominates the value of our dependent variable. So let me give you an example why we need feature scaling. So for example, this is dependent variable and these are the independent variables. So profit depends on R&D speed, administration, marketing spend, and what state it is. So let us say the state dominates this all uh, independent variables, right? But it would be a very bad regression model if only one predictor or feature dominates over other. It will be very bad if only one feature dominates over the other features, because it will disturb the value of our profit. So we use feature scaling. To overcome this problem. So what feature scaling does, it doesn't allow the dominating feature or predictor to predict the value of our label or in a dependent variable, right? So there are three types of feature scaling: standard feature scaling, min-max scaling, and normalization scaling. We use feature scaling so that all the independent variables, features, or predictors contribute equally to find the value of label or dependent variable, right? So standard scaling. Standard scaling is used when the features are in normal distribution. Normal distribution is a symmetric distribution, is a continuous distribution in which the data points are more towards the middle rather than the extreme ends. So let me show you with an example. So this is a normal distribution graphs look like. So most of the data points lies here, and symmetrically it reduces at the extreme ends. So this is called normal distribution. So we use normal distribution in linear regression, logistic regression, support vector machine, and neural networks. The formula of standard scaling is given by this. Standard scale xstand is equals to x minus mean to the ratio of the standard deviation of x. So the range of standard deviation is between -3 to 3. Let us say this is our regression equation, right? Y is dependent variable and it depends on x1, x2, x3. x1, x2, x3 are independent variables. We multiply a, b, and c so that we multiply a, b, and c so that one feature doesn't dominate over other feature and it equally contributes to the finding of our dependent variable. So for let's say x1 dominates over x2 and x3, so we multiply a which is less value, so that the value of this part becomes less, and it x1 equally contributes as x2 and x3 on dependent variable y. Normalization scaling. It is used when the features are not in normal distribution. This this is used in k-mean, image processing, and neural networks, right? Let's discuss this all in the upcoming videos. So the formula is the same, but instead of standard deviation, we are calculating the ratio of the difference of the x minus minimum of the x and max of x minus min of x. That means this one x1 minus the min of x. Let us say x3 is the least value, and x1 is the max value. So the normal value of x1 is x1 minus min of x is like x3, and x1 minus x3. So the in here the range is from -1 to 1. Yeah. So now min max scaling. This is similar to the normalization scaling, but and the formula is also same, but the only difference here is the min max variable is between 0 and 1. So this is the very important stuff, R square. This is where now our main machine learning is going to start. So right, yeah, R square is equal to 1 minus SS RES by SS TOT. SS RES is the residual sum and SS total is the total sum. So from here, right, from here SS result is calculated as the sum of the difference of square. So difference of square, this is our, let us say this is our predicted regression line. Yeah, this is our regression line, and these are the points on which this line is passing. So SSRES is the sum. We add the sum of the difference, the sum of all this, the difference, this point and the point just lying on this line, this point and the point just lying on this line, the difference of this point, and so on, right? We find the difference of the square, and we add it totally to find SSRES. And in the same way here, SS tot is the sum of this point and this line. This line is actually called as the average. This line is the average of all these points. So if you calculate the average of all this line is going to be the average. So the point lying on this and to the difference of this whole square and so on till all the points, the sum of all the points is what we get as SSTOT. So what R square does, it tells how much good our regression model is. If the R square value is 1, our model is perfect. But this is just seen in hypothetical situations, as we cannot make a perfect model. So R square value is, if it is greater than 0.7, it's a good model, but if it is less than 0.4, it's a bad model. If it is between both 0.7 and 0.4, then it's average model. Yeah. So R square depends on this SSRES, the residual sum. So here the R square depends on the residual square. If the residual square is less, the R square value is more, as you can see from the equation, right? Here now the adjusted R square, similar to R square, this is just improved. version of R square, right? So in this, what happens in R square is, let us say if we are adding more features or predictors to our regression model, it can sometimes get a better R square value. But we are not taking into account the features, the number of features and the number of predictors, right? So for that reason, we are using adjusted R square, because it takes into account the features or predictors that our regression model is having. So adjusted R square formula is given by this: 1 minus R square, this is the value we have calculated in here, and n minus 1, n is the total number of observations. So for example here, the total of number of observations is like 51, right? Here the number of observation is, and k is the number of predictors. Here the number of predictors is 1, 2, 3 and 4. So k value here is going to be 4. So in this way we'll get a better understanding of how our regression model is behaving. Is it good? Is it bad? How is it performing, right? Main challenges of machine learning. The first one here is insufficient quality of training data. That means the quality of the data is not that good, and the number of data that it's receiving for training is not in a large scale, right? Let me give you an example. There is a mango, and if you point out this mango and say to a person, so this is, to a human, this is a mango, and that person will really instantly understand what a mango is. But for a machine, you have to give like many types of mangoes: the red, the yellow one, the red one, the green one, and many types of mangoes, and then only it's going to understand. If you just pass only one mango, it won't understand. If it won't understand what a mango looks like and what the types are. So machine is a really dumb thing, right? So the second part is poor quality of data. So if the data has lot of errors, it has lot of noise or outliers or missing data, then the data is of poor quality. So let me give you an example. What is an outlier, right? So yeah, see here, this point is not at all in this line, it's very far from this line. So this line reduces our ability to make a regression line. So this data is called as outlier. So because this is very far from our predicted value, and this is very far from our data points here, right? So, and if also our and also if our data is containing some missing data points, for example here you can see, yeah, so the data here is missing, here and here and so on in the middle. If this is happening, then it's really bad quality of data. So the third one is irrelevant feature. So what happens sometimes, for the dependent variable, not all the variables are important and relevant. Some of the features are irrelevant. For example, let us take this example, right? To find the value of our profit, we don't need the value of what administration has to do, right? Sometimes we don't need, for example, we don't need the administration to do anything with the profit. So we can take off this this feature, because this is not helping in calculating our profit. It's just vague. We don't need it. So this is irrelevant feature. So now, overfitting the training data. What does this mean is the data is so well trained on our machine learning model that it won't predict the value of other data points other than our training set data points. For example, let us take this. So let us take this an example, right? So let us say from 1 to 20. So now if we give the data points corresponding to this 23 to find the dependent variable, it wouldn't be able to find, because the machine is only learned to find the values based on from 22 to 20. Only this data points is going to find the value, right? Overfitting the training data. In this, what happens is the machine learning model is very badly trained on training set. So even if you give the values corresponding, data points corresponding to training set, it wouldn't be able to find the dependent variable value. Now for example, we have trained the value from 2 to 20, right? And even if you give the values corresponding to this data points, 3 data points, it wouldn't be able to calculate the profit corresponding to 3 because it has been underfitted. Hope you find this video informative, and if you do, share, like and subscribe, because it took a lot of effort for me to make this video. So for now, signing off, Salman in Tech.